Hey guys, thank you so much for joining us today. This is our first in a three-part series of what we've pet named Lockdown Learnings. Today we're going to be covering Introduction to Profibus, and the other two sessions we've scheduled next week. Tuesday we have Introduction to Industrial Ethernet on the 7th of April, and then on the 9th of April we've got Introduction to Modbus, so we're looking forward to running those. We've also been toying around with the idea of including a fourth training course, which would be functional bonding and grounding for industrial communication networks. I think it's a very relevant topic, and probably be sending out details of that later today, and hopefully you guys are interested in joining that too. But yeah, thank you again for joining us. We're excited to host this event. Unfortunately, this is quite a challenging time in our history, and I think that challenges and disasters breed innovation, change way of doing things as well. So we hopefully we're going to be doing a lot more online training courses like this, and hopefully we can impart some knowledge today. My name is Roos. I'm one of the few trainers and service engineers at Industrial Data Xchange, or IDX. I work with a couple of colleagues in the academy, Bruce and Sean. We generally work with Profibus and PROFINET a lot when we're not offering certified engineers courses on site. We are, or in our academy, we're often on site doing audits, call-outs, and we've seen the worst of the worst problems that you can get on these communication systems. So if you guys have any questions, please do drop mails to academy@idx today, and we'll happily respond to any of them. All right, so today is the first part series, Introduction to Profibus, and we're quite excited about this topic. For those of you who have noticed, at the bottom, my slide counter says slide 1 of 412. Don't have a heart attack, it's just a bit of a joke. Although Profibus can be covered in 412 slides quite easily, so I do invite all of you to definitely jump onto some engineers courses after this. There's plenty we can chat about, everything from design all the way up to advanced troubleshooting and auditing. But today should give you a good overview of Profibus, what goes into Profibus, what is Profibus, what are the benefits of Profibus per se, and yeah, I'm excited to take you through it. The topics I'm going to discuss today: what is Profibus, some of the properties and operations of Profibus network, transmission technologies used to transfer the protocol, so we'll talk a bit about the electrical medium that transfers the bits and bytes, as well as fiber as such. I'll take you through a couple of slides of identifying and correcting common network failures, diagnostic tools and remote monitoring solutions, and then lastly I'll finish up with some certified training and further proactive steps that can be taken. So where do you go from here? One topic that one slide I do enjoy going through. This slide helps to better explain what IDX does exactly, but also it helps to put context into the topic which we are discussing on the day itself. So today we're going to be talking about Profibus communications. Profibus communications are designed to connect controllers to field level devices and sensors out in the field. It also has the capability to allow inter-control system communication. What this slide shows is the various different data communication systems that can be identified on a site. How IDX typically adds value to our customer base is creating a bridge between all the different disparate communication layers, and enabling efficient communication between all these different channels, all the way from field level devices up to IoT type solutions. So now, first step, what is Profibus? So to start off with, what is Profibus? I have here a sort of an example network layout of Profibus. Profibus is a digital communication system for field devices. It's used quite commonly, especially in the South African environment or mining industry, manufacturing industry, and throughout the whole world. It has been one of the most popular industrial communication protocols and the most successful and well implemented. and is still very readily used in multiple different industries. The communication with Profibus is two-way, so devices can receive information from controlling stations, but can also send the information to controlling stations. The data that's sent via Profibus could be simple inputs and outputs, but it could also be advanced or sophisticated communications from things like VSDs or process analyzers. So on this sample diagram over here, you'll see a couple of things. So the top here we have something called masters. So masters are the controllers I showed in the previous slide. They control communication on a Profibus network. A master would typically have a program in him that allows him to do a certain function. Whether that function is to read inputs, make a decision on them, and write outputs, or even to just read the inputs and log that in a database for management reporting or for future use. We have slave devices. So slave is a term for any useful device on a Profibus network. A couple of examples of slave devices would be digital IOs, VSDs, process analyzers, temperature sensors, anything that is typically useful to be read from the plant. We have a device here called a repeater. So we'll talk about a repeater a little bit later, but it's a passive component that allows us to extend the limitations of the copper digital communication system in Profibus. An OLM stands for optical link module. OLMs are responsible for converting copper binary strings, or this electrical signal connecting all these devices, which you might know as a purple cable, and it converts that to pulses of light. Fiber optics is excessively useful when you want to run long distances across a plant. Can be useful, I think, up to about 30 kilometers between substations as such. Other benefits of fiber is that it is completely immune to interference in the field. And this can be quite a big challenge for digital communication systems. We'll chat about that a little bit later as well. And lastly, one of the things you will notice is that on each of these devices, there's something that says ADDR. That's just shorthand for address. So address is pretty important. We'll chat about that in detail a little bit later. And you'll notice that every single one of these devices has a unique address to allow it to communicate. This blue network at the bottom of here, this is Profibus PA. We're not going to talk about Profibus PA in this session. We might schedule that for a future course. But the main differences between Profibus DP, the purple cable which we're talking about today, and Profibus PA, the blue cable, is PA allows both data and power to be communicated between devices. It's mainly used in the process industry to connect things such as temperatures, pressures, as such. So why would I use Profibus? What are the advantages of using Profibus? Well, let's go back a step. How plants would traditionally have interfaced with all the machines, so sensors, actuators out in the field, is hardwiring all these sensors into a central control station. So you'd still ultimately have your control system, but you'd have to run a digital analog loop to every single sensor out in the field, whether that be a temperature or an analog output to a motor or a VSD to start a conveyor belt. And this can be a challenge because there's some limitations when it comes to the amount of data, the management of these systems, but also there's a huge amount of wiring that is required and maintenance of this wiring as well. So by connecting a Profibus system, firstly, you reduce your wiring substantially, because now instead of running a single loop for every single input and output that you require in your PLC, you can just link up a whole lot of field level devices or just distributed, what we call distributed IO out in the field that can connect the sensors with just 2 wires. So to share multiple different pieces of information, you can share the same communication system, and this communication system is what we're talking about today, which is Profibus. Centralized commissioning of devices, and this is excessively useful, or extremely useful, where from a central control point, you can configure multiple different sensors and actuators out in the field and change different parameters as you go. The type of data that is given by field bus type systems like Profibus, it's not just necessarily the 25 degrees Celsius that you're getting from the temperature sensor, but there's a huge amount of diagnostic data that's available in these systems and a huge amount of parameter data to set up and configure devices to meet your requirement. Flexibility in the system, for sure. If you wanted to add on a few more sensors out in the field, you don't have to go and run a whole lot of new analog input wires across the entire plant. You can simply just add another analog input card onto one of your distributed I/O and configure it in the PLC, and it's a lot easier to expand and change and manipulate the system to meet your requirements. And I suppose that goes hand in hand with future planning. Some of the disadvantages of field buses, and that's the main reason why we're all meeting today to discuss, is field buses tend to be quite sensitive to faults. There is quite a few installation requirements and specifications that go into these field buses. And unfortunately, if these are not adhered to, the field bus systems can cause quite a problem and can have quite intermittent communication failures, which can be very difficult to track down. There's huge complexity in these different systems, and it's very important that people installing, maintaining, troubleshooting and designing these networks understand the specification of how they're supposed to be installed. As soon as this is not understood, that's when we start getting and experiencing issues on site. I can personally vouch that a PROFIBUS system that is installed properly from the beginning will give you 15 to 20 years worth of uninterrupted and useful life, and it will not fail unnecessarily. Yes, there are those occasional instances that a device might fail, or there's other mitigating factors that can affect the network, but PROFIBUS is a very stable and well-designed protocol that, when implemented properly, works very well. And it's important that engineers and technicians working with PROFIBUS systems understand that a field bus or PROFIBUS system is not just a wire. There is specific electrical characteristics that go into installing these systems and certain design limitations that need to be adhered to ensure continued communication. To talk about some of the properties in operation. Firstly, PROFIBUS uses addressing. As we saw in the first slide, you have multiple different addresses of devices. There is 128 different address combinations you can use in a single PROFIBUS network. These are numbered 0 to 127. The addresses, I suppose you could refer to it as like a postal address or a street address. It's how devices know where the information is meant for them or not, and that they can receive to that information. It's very important that no two devices in a single network share the same address. The address needs to be unique for all devices, and you can get quite severe issues when you do accidentally create duplicate addresses within one network. The issue with PROFIBUS is that there's no concept of routing, and there's no components in the network that can direct a message to a specific device. When we refer to PROFIBUS, which stands for Process Field Bus, the bus concept of it is that all the devices share the same common media, which means that when a telegram is sent by a controlling station, every single device on the entire network will hear that telegram. Only the device whose address is specified in that telegram will respond to that telegram. So we need to be very careful to make sure that all devices have a unique address. How do I set the address of devices? There's a few ways. So a lot of PROFIBUS devices have physical switches on them and dials that allow you to physically set the address of the device. Here's the first example, which are some rotary dials. Rotary dials are pretty simple. Wherever the rotary dial points to is multiplied by a multiplying factor at the top of it and added to the next rotary dial. Some might not just be 0 up to 9. They could include a hexadecimal value up to F. But in this example, I'm pointing to 3. 3 times 10 gives me 30. Pointing to 1 plus 1 gives me address 31. The limitation of these specific rotary dials, I can only set the address maximum of 99, which means I wouldn't be able to utilize the full complement of 128 addresses in this instance. More commonly though, we see binary switches on PROFIBUS devices to set the address. You typically see switches 1 up to 7. Each of these switches have a specific value to them. They're numbered 1, 2, 3, 4, 5, 6, 7, but the actual value of these switches would be 1, 2, 4, 8, 16, 32, and 64. Typically, any switches above binary switch 7 are used for additional functionality on the device. That might be, for example, to put it into redundancy mode or enable some sort of manufacturer-specific mode in it. Quite simply, you'll see that there's a little on symbol over here. If the switch is turned on, then the binary value of that switch applies and gets added to all the other switches. In this example, switches 1, 2, 4, 8, and 16 are all enabled as on, which means I add these all together to give me the address of 31. The third way which we can set addresses is using something called a class 2 master. That allows us to change the address of a device over a PROFIBUS network using a specific class 2 master telegram. This is typically for devices that don't have switches on them. And then above that, you would get some devices with LED displays and some third-party programming software. But these are the most common ways to address devices. Some good addressing practices, which we could consider to install on site. Maybe I can give you the challenge here of why we need good addressing practices. Say that you plugged into a PROFIBUS network with a diagnostic tool, and your diagnostic tool leads you to believe that device 2 is experiencing issues in the network. So now you as the PROFIBUS engineer want to go and identify where is 2. If you plugged into address 1, you kind of expect 2 to be the next device on the network. More often than not, it is not like that. You find that addresses are haphazardly set on devices, and there is no order to how addresses are set. So I'm going to suggest 3 different ways in which you can set the addresses of devices on a network. So consecutive addressing is where I would set my PLCs or my controlling stations to the lowest possible address. And then as the cable goes down the line, you increment that number going up to a higher number. So in this example, I have a single PLC. I've set them to address 1. After him, I have an IO station, which is 2. After him, I have a BSD, 4, 5, and so on and so forth. So that if I had to follow the cable, I know that the next address would be 2. Another way of addressing would be addressing by areas. Typically, your PLCs again would be at the lowest possible addresses, so address 1. All right. If you have multiple PLCs, it could be 2, 3, 4. And then if, for example, your network is distributed across multiple different substations, you could assign specific numbers to those substations, and this would allow you to know which area of a plant is failing or which area of a plant needs maintenance and how to change it. So for example, in substation A, I can set all devices in that substation the 20s, substation B could be the 30s, substation C could be the 40s. I could do addressing based on function. This might be useful if you have a couple of different panels and each panel has a different function in the plant. Again, my PLCs are at the 1s, maybe all my IO stations or input-output cards are at the 20s, all my motors and variable speed drives are at the 30s, and maybe if I have some panels out in the field, remote IO stations or RIO panels, those can be set to the 40s, and that can also give me an indication of some order on the network as well. So you might be asking, well, you said that the PLC should be at the lowest possible address, which you've indicated here as 1, but we can use 0 as well, can we? Not really. There's actually reserved addresses in PROFIBUS as well. These 3 reserved addresses are specified in the protocol documentation, and they're reserved for additional functionality on the network. Address 0 is reserved for diagnostic or class 2 master stations. These are tools that allow us to enable or to conduct configuration on networks and to do things like set the address of devices across the network. Address 126 is a default address for new devices. You should never leave your devices on your live network at this address because it's very easy to accidentally create a duplicate address and cause problems. Typically, if a device does not have the dials to set an address, but actually is set always by a class 2 master or by some additional software supplied by the manufacturer, you would have the default address 126. You should change this address to a live address in the workshop before connecting the device to your network. And 127 is a broadcast address. When a controller transmits a telegram to 127, all slaves will listen to it. Slaves can be categorized into groups, and depending on the group, they might action what the master is doing in that broadcast address. Examples of why we would use broadcast addressing would be maybe starting multiple devices at once or stopping multiple devices at once. And there's a couple of other useful cases such as synchronization. How a Profibus network works. Well, there's a term which we use in communication systems called half duplex and full duplex. Profibus is an example of a half duplex system. Half duplex means that I can listen or I can speak, but I cannot do both at the same time. A full duplex system, for example, Ethernet, means that I can talk and listen at the same time, and this is typically why Ethernet is substantially faster than field bus-based systems. But Profibus is half duplex, which means that only one device on the entire network can talk at once. If two devices talk at once, this is going to create communication issues. So the protocol requires that the master controls communications on a network. What happens is that all other stations or slave stations will remain silent until the master has sent a request to the slave devices. Once the master sends a request to a slave device, the slave device will respond with any data that the master has requested, or just respond to say, I have actioned the command which you have given me. Thereafter, the master will move to additional station addresses. You get two different types of masters. You get class 1 masters and class 2 masters. A class 1 master is typically your PLC, programmable logic controller. It's the device that is a program that simply reads inputs, makes a decision on those inputs, and writes outputs. Class 2 master is used for diagnostics configuration on the network. A slave station, as I mentioned, is anything that's useful to you on your network, such as input and output modules, temperature sensors, motors, and so on and so forth. The information sent between the stations can be configuration data to configure devices to behave in a certain way, diagnostic data so that a device has a mechanism to report something that has gone wrong with it. There's a huge amount of diagnostics that are implemented into slave devices, and I definitely do suggest that this diagnostic information should be used to the full advantage by the PLC programmers. You could get, for example, diagnostic information from an entire device, from a single card on a device, or even from a single digital input where you can feed you information such as short circuits or high value or high low value as such. And this will all be available in a configuration file, which we'll talk about in a minute. But then obviously the main function would be process data, so sending data through the network. Typically on a network, this is an example of a Profibus network where we have a single master or PLC, and we have 4 slave devices, and a half duplex or cyclic communication goes from device to device. The master will always start at the slave device with the lowest possible address, and will move to the highest address until he moves back to the lowest address again, and he increments device by device. You can see that he sends a request and waits for the response, sends a request and waits for the response. Now, here's where you could possibly understand the challenge by creating a duplicate address. When the master sends his request to device slave 1, if slave 2 has the same address as slave 1, both of these devices are going to respond at the same time. They're going to corrupt each other's telegrams, and it's going to end up causing possible network trips or failures. You can have multiple masters on a single network, but again, because they all share the same bus system, only one device can communicate at once. So because masters control bus communications, they need a different mechanism to decide which of them is allowed to speak. They use what we call a virtual token, where the master 1, or the master at the lowest address, will first communicate to his slave devices. He'll pass the token to the second controlling station on the network, who will then conduct any communication that he requires, and he'll pass the token back. And this is what we call a multi-master system. To set up a Profibus network is pretty straightforward and made pretty easy. Now, when Profibus was developed, it was developed by a whole lot of vendors and organizations with the intention to allow for multiple vendors and manufacturers to share the same communication system. So now you could have devices on a single network from multiple different vendors. So for example, here we could have a Siemens controlling station, and we could have a few other vendors which are manufactured here. But this Siemens controlling station needs to be able to know what are these devices, what can the devices do, and how can I communicate with them, what can I do with them. So therefore, when a manufacturer develops a device, they have to also create something called a GSD file. A GSD file is pretty much a text file that has a description in it of the device's capabilities, how to configure the device, the diagnostic data available in the device, and what actual physical data the PLC can read from that device. When you connect the device to the network, a couple of configuration steps are required. Firstly, you need to load the GSD file into a configuration tool. This configuration tool would be supplied to you by the manufacturer of the control or the PLC. You would need to set and say what are the addresses of each of the devices. And then you actually need to do some parameterization where you would say, how have I set up this device? So in the bottom left over here, you'll notice, excuse me, there's a I/O module. And within that I/O module, here's multiple different cards. Here's 4 cards over here. So for example, this first card could be a 4 digital input card. Second one could be a 4 digital output card. And then I could have a couple of analog cards at the end over here. This is what we call hardware modular, which means that physically I can change the configuration of that device to anything that I want it to be. But the PLC doesn't know that. So I need to tell this PLC what physical configuration have I set up over here. The GSD file will provide the configuration tool with all the available modules that can be added, and it's a responsibility of the PLC programmer to tell the tool, in this I/O block, I've added these 4 modules at this address. Once all the GSD files from the network have been written into this configuration tool, you've specified the addresses and parameterized all the devices. This configuration is then downloaded to the PLC. On startup, the PLC will automatically sync to each of these devices, enable communication channels, and then go into data exchange. And then that is at which point input and output data will be shared cyclically throughout the network. With regards to transmission technology, the Profibus protocol spends quite a bit of time discussing the main communication transmission technology, which is RS-485. That's the typical purple cable that you are used to seeing. And RS-485 is not exclusive to Profibus. It was developed long before Profibus, but Profibus just defines how RS-485 should be used. Right. Another common communication transmission channel would be fiber optics, which we're not going to talk about too much in this course. And additional would be MBPIS, which is the protocol used to transfer Profibus PA telegrams across the network. There's lots of other transmission technologies available, such as Bluetooth, wireless, infrared technologies. It does not really matter how the Profibus telegram gets from one point to another, as long as all the bits and bytes of the data which is transferred across that transmission medium is transferred intact. So the first one we'll talk about RS-485. This is a balanced 2-wire data transmission, which uses a shielded twisted pair wire. This is typically used in Profibus DP networks. Second one, fiber optics. You get plastic or glass fiber with multiple different qualities, which can allow for interference-free communication with full electrical isolation. And the last, which we briefly spoke about, MBPIS, is used in Profibus PA. It can be used in intrinsically safe environments as well. Talking about RS-485, here's a cross-section of a Profibus DP cable. We can go through the cable quickly. So on the outside of the cable, the purple wire, which you've probably seen in a lot of your cable trays and racks on site. This can be UV resistant, chemical resistant. It could be an armored cable for bearing it underground. Obviously, using the cable which meets the requirements or environment that you're in makes sense. Below that, there's 2 different shields. There's a stranded shield and a foil shield. The stranded shield and foil shield are designed to pick up any interference that is injected on this cable and drain that to a grounding point. It's designed to protect the electrical signal which is traveling on the PROFIBUS A and B cores. With the shield, we're going to speak about this in a lot more detail during our functional bonding and grounding course, which will probably be running week after next. But a couple of important points: the shield needs to be continuous throughout the whole segment. Every single segment needs to have continuity of the shield. The shield is typically joined inside PROFIBUS connectors at devices. At those devices, the device also has a mechanism to drain any noise that is picked up on the shield to ground, typically through the DIN rail or from some other functional grounding points on the device as well. The two colored cores inside here, you actually get two different types of, or main categories of PROFIBUS cable. You get stranded core and solid core cable. Main differences between, or use cases of stranded and solid. Stranded core cables tends to be quite a bit more expensive. It's used in mobile environments. So for example, if I'm using the PROFIBUS cable in an energy chain or something where the cable is experiencing a lot of vibration and movement, stranded core is necessary because it won't break as easily. Stranded core, you have to use screw type connectors to connect it to devices and plugs. For solid core tends to be one of the most common use cases in the environments that connect PROFIBUS cables. It is cheaper, it needs to be used in static environments, for example in panels or cable racks and trays. You can use fast connect plugs, which makes setting up these cables a lot easier, as well with solid core cable. And then lastly, there's a substrate around those cores. He maintains that twisted pair. Now, on the previous slide at the top here, I said it's a shielded. We've spoken about the shielding, which protects the cable from electrostatic interference and any noise and interference induced on that cable. Twisted pair, so it actually has a twist throughout the entire cable. This is actually very important. It's very important to maintain that twisted pair throughout the network. The twisted pair protects the cable from magnetic fields. As we would have learned in high school physics, when you have magnetic fields near a conductive object, it causes a charge to flow in that conductive object, and that is extremely bad news for digital communication systems. So by creating a twisted pair, the adjacent loops cancel out the concurrent charge that is caused to flow in each of the copper cores. PROFIBUS baud rate. Baud rate is another name for bit rate or network speed. This is configurable on a PROFIBUS DP network. The speeds which you could set a PROFIBUS network is anything from 9.6 kilobytes per or kilobits per second up to 12 megabits per second. I've highlighted 1.5 megabits per second because this is the most common network speed that is set up on PROFIBUS DP networks. If you have to ask anybody why they would use 1.5, the real answer is that it's the default network speed set up in PLC programming software. So the PLC programmers typically don't change it. The network speeds do have a bit of an impact on how the network performs, and there's obviously limitations that get increased on the network the faster that you run it. Most modern slaves will support or auto-detect several different data rates. So that means that if I set up my PLC to run at 1.5 megabits per second, as soon as he starts up on the network, each of the devices will conform to that or respond at that network speed. Now, your question may be, well, if 12 megabits per second is the fastest, doesn't it make sense just to have very quick cycle times? Why don't I just run my network at 12 megabits per second all the time? Well, as I mentioned, this creates, I suppose the best way to describe it is an amplification of installation failures and faults on a network. So things such as impedance mismatches, which could be created anything from stub lines to using uncertified devices to installing the cable outside of specification. Noise, which is a word to describe interference that is picked up on the network from high voltage cabling or noisy devices such as VSDs, motors, or installation faults. If I'm going outside of the range of the PROFIBUS specification and having a segment that's too long, for example, these fault will get amplified the faster that you run the network. So advice is that you should run the network at the lowest possible speed, which is tolerable by the process. The PLC programmer would typically be able to make this decision, generally based off device user manuals and manufacturer requirements. It will define how fast the network should typically run. And I find 9 times out of 10 networks are running a lot faster than they necessarily have to. That being said, it is not a way to fix a failing network by slowing down the network to try and correct the issue which is occurring on it. But if you can run a network at 187.5 kilobits per second instead of 1.5 megabits per second, and it's installed according to specification, your network will be better off for it. Some examples of where you would have to run your network at faster speeds, for example, would be if you require precision motor control. Typically, a lot of the automotive manufacturers require a faster network speed if they're controlling some welding robots or assembly robots as such. But if you have a process environment where you are just reading temperatures and pressures, running a slow speed typically would not be an issue. Network baud rate or speed also affects some of the ways which we install the network, and the first of this is how long a segment can be. Now, to start off with this, let's define what a segment is. A single Profibus network can be configured of multiple different segments. So I can have one network with 125 devices, or however many I'm allowed to, but that network can be built up of 10 different segments. A segment is defined as a continuous piece of copper wire, so a copper wire that has continuity with it. All right. Segments are separated by only 2 things, which are repeating stations or optical link modules. So fiber optics and repeaters split my segments and create new segments. I would need to create segments, new segments, for a few different reasons. So firstly, if my segment length exceeds the requirement based on the baud rate, if the number of devices which I'm allowed on that segment, which we'll cover in the next slide, exceeds the number for that segment. And I can also use segmentation to help isolate noisy devices off different sections of my network. We'll discuss isolation in a little bit of detail shortly. So, for example, if my favorite baud rate, 1.5 megahertz per second, is utilized, then I'm only allowed to use 200 meters of copper cable between repeating stations. So after I've installed 200 meters of cable, I need to put a repeater in the network, or I need to install fiber optic modules to enable me to start a new segment where I have an additional 200 meters. Going longer than this 200 meter rule, typically the effect of attenuation digs in, and you start seeing that the signal quality being transferred on the network gets degraded substantially. And that's where you'd start finding intermittent communication failures. The second limitation on a segment is the maximum number of devices I can have is 32 devices. This is not actually a Profibus limitation, this is an RS-485 limitation. You'll find the same thing in an RS-485 Modbus network. You can only have 32 stations on a single segment. After that, the stations tend to have a excessive impedance mismatch and imbalance effect on the network, which then requires the use of repeaters or fiber optic modules. I also wouldn't live on the edge either. Wouldn't put 32 devices on a single segment. I'd probably drop it to like 25 or 24. This just allows for future expansion. So maybe if you want to connect an additional device in at a later stage, then you have some room to play. Or even if you have your one of your site engineers do an audit in the network, he plugs in the testing tool. The testing tool still falls part of the 32 devices on a segment. Here's an example of a typical Profibus repeater. A repeater is a simple device. He takes in a signal on one side. He boosts that signal, squares out the level of the signal. Some of them are clever enough to do sort of what we call bit interpretation and correction, which means that if a bit starts getting deteriorated and changed, he can correct that bit. He would take that incoming signal, boost it, and transfer it out on the other signal. This is an example of a single channel repeater, which just allows repeating to one more segment. It's very important to note that when connecting a repeater like this into your network, you come in at the top on channel 1 and you go out at the bottom on channel 2. I've seen a couple of instances where it gets installed that channel 1 gets connected over here and they expect channel 2 to be over here, which is not the truth. This actually just ends up becoming an expensive chocolate block or terminal block, which will have no repeating effect on your network whatsoever. You'll see that there's a sub D9 connector on this device as well. That's very useful as you can connect a testing tool or configuration tool into the network, and allows you to see what's going on this side of the network. Here's an example of a multi-channel hub. So instead of just having one repeating channel, in this case you would have 6 repeating channels. Hubs like this are very useful for creating segmentation, as I spoke about earlier, if you want to isolate noisy segments on the network. It also allows you to create a star-star type topology. If, for example, you're in a substation and you want to spur out into multiple different cabinet arrays as such. And the ultimate function of a repeater, taking in a noisy signal, correcting that noisy signal and pushing out a nice clean signal. It also provides optical isolation between the different segments as well. So if you do get some sort of surge or something on one of your other segments, this should not affect your expensive control systems or valuable control systems. Now, the next thing we need to chat about, and if you do learn anything from me during this course, it'll be how to terminate properly on a segment. Terminating or not terminating properly on a segment is the #1 cause of failures in Profibus networks, and it's a very simple concept to get right. So what I mean by terminating is, typically on a Profibus network, there's a lot of energy that's injected onto the bus. Right? So when one of the stations sends out a telegram, this energy or binary string transfers along the bus, and energy can't just disappear. When it gets to the end of the bus, so it has no more continuity of copper cable to go anywhere, all it's going to do is this is going to reflect and bounce back down the line. Now, this reflect, what we refer to as reflections, interferes with future communications or telegrams going along the bus. And this can be a very bad issue for networks and creates quite severe communication problems. So in order to correct this, what we do is at the ends of the network, because you always have 2 ends on every single segment, so in every single segment it's important to connect terminations, we put a series of resistors, and what this resistor does is absorbs that energy that's being transferred on the bus, and it should absorb it right to 0. Okay. Typically, terminations are enabled with connectors like this one over here. So you can see I have one cable going in, so obviously this is the end of my network. So I enable a switch in it, that is actually my terminating switch. And what he does is he redirects the signal to a set of resistors. You'll notice that these resistors have a 5-volt current traveling into them. This 5 volts is very important. Profibus uses something called an active termination, which means that it requires the 5 volts in order for the termination to operate correctly. The 5 volts does not come from the Profibus cable, and it actually comes from the device that the connector is plugged into. So it's very important that that device is powered, because if it's not powered, it's not going to be supplying this 5 volts for this termination circuit. Simple way to remember where to terminate: if one cable comes into a device, you enable the termination. If 2 cables go into a device, you do not. So there's no need to add resistance to the segment where you still require the energy to transfer further down the network or bus. The termination circuit consists of 3 resistors: a terminating resistor in the center of 220 ohms and 2 biasing resistors. This biasing resistor circuit just steps up the idle voltage of the network to 1 volt. That helps to make the network a little bit more resilient to network faults and interference, but it's also mainly used to allow Profibus to run to its full network speed, which is 12 megabits per second, because typically RS-45 is not designed to run up to 12 megabits per second. So it's very, very important to ensure that your termination circuits are always powered. Here's an example of the reflections, which we were referring to earlier. You have all this high volt energy traveling down the bus. Once it gets to the end of the cable, there's nowhere else to go. That is going to go forward and cause future issues like an echo. Now, what happens in a situation? Well, this is an example of a network. So I've got my PLC. I can see there's one cable going in here, so I need to enable the termination on the plug or the connector at that point. And then this is the other side of my segment. I've also got one cable going here, so I need to terminate there. So everybody would agree, got 2 termination points. Every single segment needs to have 2 termination points. Even if a repeater is the end of your segment, you need to terminate the repeater because the repeater is the end of the segment. Now, what happens in this network when address 5 or slave 5 is a motor? It's a VSD, and that VSD needs to be locked out by electrical maintenance because they want to do some maintenance on the motor in the field. You still want to run your operation with these 3 slave devices, but this definitely has to be powered out for safety reasons. Now, as soon as you power down that device, what you're going to do is you're going to lose your 5-volt circuit, which is supposed to be traveling along there. And this doesn't make the network very resilient, and it becomes a bit of an issue. So what we can do is we can actually install a dedicated terminator device, something called an active terminator. This is just a simple component that has its little 3 resistor circuit installed inside it, and he should be powered 24/7, maybe by a UPS or a dedicated power supply, possibly even the same power supply that powers the controlling station or the master. Now, instead of making my last slave device my terminating point, I daisy chain out and go straight into an active terminator. This is an example of an active terminating device. You would typically wire your Profibus network into these bottom 3 pins, supply them with a dedicated power source. And what he also does is he creates a connection point for your testing tool to be plugged into the network. It's very useful to have connection points in every single segment, because when you want to plug in a testing tool, you actually want to look at the actual true electrical quality of that segment itself. So it's important that when you connect, we actually use oscilloscopes in Profibus networks to analyze the true health of the network. And it's very important that you can connect into every single segment so you can get a true snapshot of that segment itself. What I look at on one segment might be very different to what I look at on another segment. So here's an example. I see over here I've actually got 4 different Profibus DP segments. So here's my one segment separated by fiber optics. Here's my second segment, my third segment, and then there's a repeater which creates a 4th segment. So the interference or noise that I'm seeing at this point, or if I connect my testing tool, my oscilloscope at this point, the rest of the network is disguised by the optical isolation created by the fiber optics. So it's important that if I want to get a true health quality of this entire network built up of multiple different segments, I need to connect my oscilloscope into every segment. And I'll show you in a minute what I mean by oscilloscope and the type of tools you can connect into these. But the main reason for this diagram is to show how it all comes together. So here I've got a few RS-485 segments. So here the purple cable is my RS-485. Here's my 2 master stations using an active terminator, and then the little yellow block indicates my other termination. I've got fiber optics linking the different sections of my plant. This is actually what we call a fiber ring, which is a redundant ring, so that if any of these fiber links break, I have another path to enable communication between the different sections of my plant. Here are a few slave devices. You can see that a repeater is connected in the middle of the segment over there. So he's creating a new segment, which needs to be terminated on both ends. And then here I'm integrating a Profibus PA segment as well into my network, but that's outside of the scope of our discussion today. So identifying and correcting common network failures. This is such a long topic, and it's one that we can spend hours and hours talking about. But what I'm going to do is I'm going to highlight some of the common issues which I see very often on site, and show you how I would typically go and identify those issues on the network. So here, next to me, I have my Profibus training rig. On here I have a few slave devices. So over here you'll see this is actually something called a Combrix. It's for monitoring. It's not a slave device. You have an input-output module, the gateway module, and then this is a CONVERSE Rev Pi gate as well. So these are my 3 slave devices on the network. I think I've addressed them 11, 12, and 13. And then this device over here that says PROFIBUS Ultra, that's actually a testing tool, but it's also got a master simulator built into him. So he's acting as my PLC or my master controller on the segment. So he's going to help me out just to show you a couple of things in the network. And you'll see this little cable at the top over here. What I've done is I've connected onto the back of one of these plugs, and I've exposed my cores on the network as well as my shield. And this will allow me to short out the network and show you the effect of wiring shorts on the network. Very quickly, one thing I didn't mention, you'll notice that there's a red and a green wire. So in your Profibus cable, you typically have 2 cores, red and green cores. The red core is typically always your B line, which is your positive line, and the green core would be your A line or your negative line. Easy way to remember it is I think of bread, B red, so B for red. You should conform to always connecting the red wire to the B terminal of your devices throughout the entire segment. It can be very bad news for a network if you accidentally swap that over and connect A to B and B to A. So, as I mentioned, the most common cause of network failure would always be terminations. So having a missing termination, the example over here, you have a plug that's plugged into a controlling station. You can see that that switch is at the bottom, which indicates that the switch is off. It should actually be on because I only have 1 cable coming in here. Over-terminations, that is also a possibility. I find it very common, especially on BSD devices, that terminating resistor is enabled somewhere in the middle of the segment. And this can be quite a big problem because you are adding resistance in the middle of the segment. It's actually going to end up absorbing that signal, which requires a bit of power to get through all the devices. And then obviously we discussed an unpowered termination, which means that the termination is not connected to a powered device or the device is disconnected. So here's an example of an unpowered termination, and although the site had enabled the termination switch on this plug, the plug was unplugged from a unused device at that point, which meant that this termination was not very effective at that point. So what I'm going to do quickly, here I actually have the page for my Profi core. You can see here's my master. I've got each of my slave devices, 11, 12, and 13 that have been configured. I'm going to use this to show the examples of missing termination. When I mentioned that we use oscilloscopes to typically diagnose or look at the true health of a network, the scope which I'm showing you in front of you, this is actually the Profibus signal. This is the binary signal that is traveling through that copper cable, which has got the request from the controller, and then it's got the response from the slave device, which is traveling through. You expect to see this to be nice, square, and even. You don't want to see any distortion on it, and you want to make sure that it has a good amplitude. Amplitude being the difference between the peak and the trough of that scope image, which is summarized nicely by this bar graphs. The required amplitude, which I expect for each device in a Profibus segment, should be below 7.2 volts, but above 2.5 volts. So this network looks like it's pretty much well within specification, sitting below 7.2 and well above the 2.5. What I would typically find, so what I'm going to do is I'm going to remove a termination switch on my network quickly. So this is with 1 termination missing. Now you can immediately see the reflections which are traveling through the bus has distorted my signal. And what you also might notice is that my amplitude has gone completely out of range. If I disable a second termination, you can see that that voltage completely jumps up because now it's going well outside of the range of what I require on that network. And this is causing severe issues. So enabling my 2 termination switches shows the necessity to keep that nice, neat, even waveform as well. I can see risk voltage low limit. Okay, that's fine. I spoke about the idle voltage. So here's my idle voltage in the center over here. This idle voltage should be sitting at 1. If I have an unpowered termination somewhere in the network, you'll see that that idle voltage drops to 0.5 volt. And if I were to remove 2 or unpower 2 terminations, that idle voltage would drop to 0 volts. That's going to go against the Profibus specifications and create a bad situation for the network. Right, and the next one, wiring faults. Wiring faults are also a very big cause of failures on a Profibus network. Typically, wiring faults are normally created within a Profibus connector, which has been wired badly. Most commonly, I find that either the A or the B lines have not been properly screwed into the terminals, but more often than not, the stranded shield accidentally shorts out one of the A or B lines. So to identify these faults, again, use your oscilloscope. The oscilloscope you should be using you can use something like a PROFITrace that has an integrated oscilloscope, or you can use an oscilloscope that has 100 megahertz frequency range, but is also a dual channel oscilloscope, which allows you to look at your A and B lines separately. It will allow you to identify which of these lines have possibly been shorted out by accident. To try identify, now when you have a wiring short in the middle of a segment, this can make the entire segment look completely disastrous. So a lot of the times I use isolation to help isolate the different faults by disconnecting certain sections of the segment to see if that problem goes away. Helps me to identify the exact device where that wiring fault was accidentally created. So back to my oscilloscope or PROFITrace software. If I dial in here to my scope image and I drop down here, I can look at 2 of my each individual cores. So this is my B line at the top over here, and this is my A line at the bottom. So if I go short out the B line, for example, you can completely see that it's flatlined. I've shorted my B line, my red core, to ground at this point. But what you'll notice is that communications are still healthy. Everything is still communicating. So ultimately, this network is actually running off a single copper core. Not well within specification, and it's probably likely to fail very soon. But this helped me identify, okay, I must have created some sort of wiring short somewhere on my network that has caused a failure on that segment. And I just tripped my network by accident. Cool. Some other very common causes of interference, and unfortunately not very easy for me to simulate from my setup here, would be something called EMI, stands for electromagnetic interference. This is caused by running your Profibus cable close to high voltage cabling or very noisy devices such as VSDs or large actuators, turbines, arc furnaces. And this causes interference on the network. So typically we need to ensure that our Profibus cable and network is always separated by at least somewhere between 10 to 20 to 50 centimeters, depending on the type of interfering cable that is connected here. So in this picture, for example, you can see that the installers have run a Profibus cable inside steel conduit, which is great. Steel conduit allows you to run right next to your high voltage cabling. And this high voltage cable that is coiled at the top of here, this is 380 volts, which is used to power a actuator at a water reservoir. So now the challenge which we have over here is that although it's been run in steel conduit over here, when it comes out of the conduit, it's coiled right next to the 380 volt power supply to the actuator. And because it's coiled, you can see it's creating a nice big transformer over here, a nice big inductor. And this creates quite severe interference in the network when that actuator is engaged or current is loaded onto that segment. And we see this very commonly on site. So very important to separate your Profibus or all communication cables by at least 20 to 30 centimeters from your interfering cables, your noisy devices such as VSDs where possible. And another very common one would be cable length. We spoke a little bit earlier when we were talking about the limitation on RS-45, that you limit it, for example, at 1.5 megabits per second to a maximum of 200 meters of cable. So ensuring that you use repeaters when your cable becomes a bit long to extend the network, and avoid having excessive cable unnecessarily in a panel as well. A couple other cables, or a couple of other faults, sorry. So at the bottom here, you can see your PROFIBUS cable. The cause of failure on this plant is this cable is actually running right over a walkway or a gangway, and plant operators kept walking past it, stamping on the cable, ended up damaging the cable and causing a network failure. So protect cables that are running out in the field, especially from high voltage cabling as well. If you have some RIO panels or remote IO panels that have a certain IP rating in the field, make sure that those panels are maintained, always closed out in the field. Check the rubber ceilings and the doors to make sure that that hasn't deteriorated or broken. I've seen some unnecessary breakdowns that are caused by coal dust getting caught up in a device and actually shorting out the electronics. So some of the useful tools that can help me to identify faults. I showed you on the PROFITRACE software earlier. I look at the scope image. The scope image should be nice and square. This will help me to identify wiring faults, as I demonstrated with the short circuit. Termination errors, as I demonstrated with the reflections. EMI, you would see a lot of rippling coming throughout the network. Earthing issues. This would look pretty similar to EMI. You would actually see the noise being induced on that signal directly. And impedance mismatches, which are created by running the cable outside of specifications, can be identified from the scope image as well. The signal amplitude, which is the height of this image, which needs to be between 2.5 volts and below 7.2 volts, is a good indication if we have, for example, attenuation. Attenuation is when my cable is too long on a single segment. This scope image in the bottom left over here is an example of cable attenuation, where you can see there's almost a shark fin type look of the scope image. But what you also notice is on the bar graph, which is the summary of the scope image, very low voltages below that 2.5 volt range. Impedance mismatches, if you install stub lines or if you enable a termination of your segment, you'd also see very low voltages. And faulty device interfaces are often indicated by the odd one out within the bar graphs and scope images. So diagnostic tools and remote monitoring solutions. Unfortunately, a multimeter is not a very good diagnostic tool for a PROFIBUS network. Great to check the power supplies, but because it's a high-speed digital communication system, you actually need an oscilloscope to capture that image, or possibly a bus tester to allow you to have a look into that network. You're pretty much blind without that. And I would never go to site without having one of those testers in my backpack, so I can actually connect into the network, have a look at what is the true health underneath a network, and not just judge it on face value. This being said, I also do not take away the value of walking up and down the network, inspecting the installation of the network, making sure, for example, that the cables below 200 meters, the connectors wiring standards are good, and very importantly, checking that your PROFIBUS cable has been separated from any high voltage cabling or noisy machines by at least 10 to 30 centimeters. So, but a couple of the diagnostic tools that you can use to help identify problems for people installing cables, or when you install a new cable run, it's often very useful to have a simple cable tester. Shouldn't be anything complicated, just a simple press a button, and he will check a couple of things. Firstly, he'll check continuity of the A and B cores. He'll check terminations at the beginning and the end of the segments. He'll check continuity of the shield, make sure that the shield is continuous. And lastly, he'll make sure that there's been no short circuits, open circuits, or closed circuits created on the network. Next one is having what we call a bus monitor. For example, the presenting PROFITRACE or Mercury bus monitor should have an integrated oscilloscope. It should be able to give you things like a live list, which can show you all the devices connected on the network. You should be able to give you a certain level of statistics on the network to tell you if there's any failures, such as legal messages and errors. Be able to give you a scope image based off it's a oscilloscope image, and then bar graphs are very useful. And lastly, Having permanent monitoring and alerting is very useful for preventative maintenance. Permanent monitoring solutions are very similar to a bus monitor, except they are permanently connected into the network. Examples of a bus monitor, such as the PROFIBUS Mercury, the one that I'm using, it gives you statistics and live values or lists. He has an integrated oscilloscope, bar graphs to have a look on the network. He also does reporting. Reporting can be very useful to create a snapshot in time of what the network looks like. So let me quickly generate a report. And you should indicate overall what the network looked like at the time of installation and give you a snapshot. This is very useful to keep on file. Reporting is definitely a critical part of auditing a network and checking overall network health. And something that's pretty useful is having DP master functionality, which allows you to go into data exchange with devices, but also to test your engineers and technicians in the workshop, simulate certain faults, and see how the effect is of those as well. For remote management, using something like Combrix is very useful, connects into your network, and he reports information on the network over Ethernet with a live web page or sending you email notifications on failures on the network as well, or even integrating directly into your SCADA systems via OPC or some other form of mechanism. So, certified training and further steps to be taken after this. I definitely invite all of you to jump on one of our certified PROFIBUS installers and engineers courses. Our installers courses typically run over 2 days and the engineers course over 5. We'll go into a lot more detail on PROFIBUS and a lot more in-depth discussions on PROFIBUS and how to properly diagnose these issues. I suggest getting training on future technologies to be installed at your plants, such as example of PROFINET, whether the industrial Ethernet protocols you might be installing. Understand how your devices work. Know where the user manuals are for those devices. If LEDs are indicated on a device indicating some sort of failure state, ensure that you are aware of what that means. Statistics and logs from a PLC. From your PLC or controlling stations, it's very useful to be able to retrieve the statistics from that device, which indicates where a network might have failed. It helps you to dial down into what an issue might be. My first step walking onto a site would be, do you guys have a history of what the faults might be occurring? Is there a particular device that is showing up, what particular segments that's showing as a failure in that section? Fault finding, experiential learning. So there's only so much that you can be taught in a classroom or even on a live webinar like this. What we have found extremely useful is if you follow around an experienced PROFIBUS engineer on site in a live environment, a lot of knowledge can be parted to your maintenance staff, to your sales engineering team, by working with that engineer to identify faults. And typically how we do this, if we do audits on a call out, all of the engineers at Industrial Data Xchange or at our competency center love to talk and love to share information as they go through the network. So possibly having a combined audit session is very useful to learn some knowledge on your specific environment and area. Invest in some testing tools like the bus monitor, PROFITRACE or Mercury, and learn how these tools work. Where you purchase a testing tool should offer you training on these tools. Obviously, the training only goes so far. You need to have that obvious base level understanding and knowledge on the PROFIBUS protocol, and then a quite in-depth knowledge on how to utilize those testing tools. At RDX, we offer free training on our PROFITRACE and Mercury kits, obviously with the requirements of users having a base level installers course. Having network audits done on your network is very useful. Audits should be done. A time frame could depend on how critical the network is or if it starts giving issues. Getting audits, you can either use a experienced third-party service like RDX. We have a couple of audit engineers who eat, sleep, and breathe PROFIBUS. But if you want to empower your staff to be able to do these network audits, having a PROFIBUS engineer certification will definitely enable you to run that audit on each of those networks. And connecting in every single segment, getting a snapshot of those networks, doing a full health analysis of the network to ensure minimized downtime. Network design, obviously understanding the full specification of PROFIBUS and the protocol requirements. We can assist with that. Where possible, you're always welcome to drop us an email at the Academy. And then obviously when things get really hairy and nasty, have a support resource on speed dial such as IDX, where we can assist you further. So my next step I would love to jump into. Thank you very much for your time today. I just want to jump straight into a Q&A session where we can go through some of the questions and jump further through it. So if you guys do have any questions, that you are more than welcome to post them. I think there's a Q&A section, and when I see the question, I can choose to publish that question and make it available for everybody, and then obviously answer it. Let me just jump back into live feed. Okay, so so Anonymous has published a question. What happens when there is more than 128 devices? So that's thank you Anonymous for publishing that question. More than 128 devices, you have a couple of choices. Firstly, you would probably need to get another PLC, create a whole new network. The other option is you can use something called a DP-DP coupler. A DP-DP coupler would act as a slave device and allows you to connect two different networks. So if you want to share information from network A and network B, you can have 124 devices, for example, on network A, 124 on network B, and share all those devices through a DP-DP coupler. But more often than not, you end up having a PLC with multiple PROFIBUS cards. And if you need more than 128 devices, or 125 including reserved addresses, you can expand that network or create a new network with a new CP card. All right. I got a question from Josephat asking, can you please give an example of a class 2 master? So let me publish that question. Very good question. Thank you, Josephat. So let me quickly jump back into my screen then, and I will show you. So an example is this PROFITrace actually has an integrated class 2 master called PROFICaptain. You'll see that there's a couple of class 2 master commands over here. So examples of these, I could do a network scan. Reinitialize my Profi core. Maybe just close down PROFITrace. I see the network didn't enjoy being harassed too much with shorting out the network as such. So bear with me for 2 seconds. Okay, so let's just quickly initialize my Profi core. Okay, so in PROFICaptain, I have a class 2 master, so I can do a Let's go online with my master quickly, going online at 1.5 megabits per second. Okay. Third time lucky. So I could do a network scan, for example. What he does is he auto detects all the devices available on the network. He feeds back things like the address of those devices, as well as something called the identity number. Identity number is a unique address, or unique ID code, which is given to every single PROFIBUS device on a network. Gives me vendor numbers. I can get the configuration of an individual device. When I spoke about the I/O card, for example, that has a 4-digital input card, 4-digital output card, and a couple of analog cards. He allows me to check what are these different I/O modules. I can check the live inputs and outputs of individual devices as well. I can fetch diagnostics from a device. So what state is that device in? Is the device healthy? And I can even change the address of a device, for example, from 11 to 14. And that is my class 2 master addressing command. Thanks, Joseph. Next question from Joseph. Is there a tool for PROFIBUS Diagnostics? PROFITRACE is fantastic. A new range of Mercury is also very good. I've had a lot of experience with them and they work pretty well. Thanks for that question. Peter asked, I would like to request the training materials at the end of the session. Not a problem, Peter. I will actually send out this video as well as my slides at the end of the session to everybody. That answers Peter's question. Anonymous said, will we receive a PDF for recording of this webinar? Yes, you'll receive it at the end of this. Thank you so much for that. Johan asks, hi Carl, how do we go about obtaining training on the network tools PROFITRACE after we purchase the item? Well, Johan, you just drop an email to Academy. We offer completely free training courses on PROFITRACE, how to use PROFITRACE. You can come through to our offices. Hopefully at the end of this, we'll have our Academy back open. But if you're all interested, drop an email to Academy if you want me to go in a lot more in-depth detail on PROFITRACE, how to use PROFITRACE, all the different sections of it, from setting up a network using PROFICaptain, and I'll happily schedule that course in the next couple of weeks. I can do that live from home at any point as well. So drop me an email on Academy if you're interested in PROFITRACE training on top of the 3 additional lockdown learnings as well. Okay. Jack, you mentioned earthing and bonding WebEx. When is that going to happen? When are you going to send out the invites? Thanks for the question, Jack. That will most likely happen. So we have this course, which is the 2nd, and the 7th and 9th, we're running Industrial Ethernet and Modbus. Possibly the Tuesday after that, I'll send out the invites this afternoon to everybody who attended this course. I think it's a fantastic topic, so we'll definitely be asking that. Anonymous asked, what is the difference between PROFIBUS DP and PROFIBUS PA? Great question. DP has multiple different baud rates. A PROFIBUS DP network can only transfer data across the network and not powering devices. Devices have to have their own separate power supply. DP is typically used for high-speed operations, such as motor control, digital inputs, outputs as such. PROFIBUS PA allows you to power devices over the network. So same 2 wires can supply data and power to devices, so you don't have to have an additional power supply. PA is a lot slower than DP, so it's typically used for environments like process industry, where you have temperatures, pressure sensors, very slow changing values that have quite a bit of inertia, so they don't change very often. PA also runs off of different types of communication systems, but typically PA is run off a DP network. So you typically have a DP network as your back level or backbone, and then you'd have something called a PA coupler, and the PA coupler would connect a whole lot of PA devices to it, but it's being controlled by a DP master. Okay. PA is also very useful in intrinsic safe environments, so environments where you have a hazardous level of explosive material, so you'd have to use something like PA to protect that section of the plant. Okay, so I got a question. The 1 passes the token to master 2. Okay, so the token is actually virtual, so it's actually just a telegram that's sent on the network. The master with the lowest possible address, say address 1, would first establish communication on the network, send his dates to all the devices. He would know what are the masters on the network because he has a mechanism of, it's called FTL status request, but ultimately has a way of pinging devices on the network to see who's there. So he would know that there's a master at address 2 because he pinged him earlier. And when he's finished communicating with all the slave devices, he'll transfer control over the bus using a specific telegram that transfers authority to communicate, called a token, to the other networks. Nick asks, with a limitation on a segment length, for example 200 meters at 1.5 megabits per second, Would that then apply to fiber segments as well? Good question, Nick. No, it would not apply to fiber segments. Fiber does not have the same limitations as RS-45 or copper segments. Fiber is purely limited by the technology of fiber you're using, so whether it's single mode or multi-mode fiber. Single mode fiber can run much further distances, requires specialized tools. It's a little bit more expensive, but I think you can run up to like 30 kilometers on a single fiber segment using single mode. Multi-mode, useful for about 3 kilometers, very useful just for optical isolation on certain sections of the plant. But yeah, it's purely dependent on the OLMs and the fiber technology that you are using. Josephat asks, is there special software which can monitor the different devices connected via PROFIBUS? Yes, you can answer that with ProfChess as a bus monitor. Less of a question, but if a system has 128 devices, could the PLC simply have 2 PROFIBUS networks with 64 devices on each? Yes, 100%. So that actually answers how you could expand it. You could actually have 2 different PLCs, each with 120 devices on them, and those PLCs can communicate with each other to share information. Okay, so the next question from Anonymous. If you take out a node for maintenance, do you need to terminate it when it is in the middle of the network, or can you just unplug it? That is a fantastic question. So the great thing about PROFIBUS is hot swappable, which means that if I'm using a PROFIBUS DP connector or sub-D9 connector, I can simply just unplug that device. I do not need to terminate. I do not need to change anything. Unplug the device while the network is operational, and the network is able to transfer straight through the plug, because the plug has continuity in it. So I can disconnect any device in the middle of a segment without interfering with communications. I can even do that with the last device, provided I'm using something like a active terminator at the end of the network. If I'm not using an active terminator and I need to remove the last device, unfortunately, I will have to terminate the device before, or I'm going to have to stop the network and rethink my strategy at that point. Okay, Warwick asks, can you give an everyday example of how PROFIBUS could be used in a mining environment, i.e. what would your slaves be? It's a great question. So, example of a mining environment, let's consider a coal mine. In a coal mine, you have lots of moving parts. You would have conveyor systems between all the different sections of the coal mine, which actually carries the product or the coal between where it is actually mined or captured to where it's stored or refined or processed further. These conveyor systems are driven by motors. Motors are controlled by something called a VSD, which starts and stops the motor. And we would typically use PROFIBUS to stop those motors. We could use PROFIBUS to read the state of the motors. We can use PROFIBUS for safety systems. So there might be a safety system along the conveyor belt, but if somebody pulls a wire, it needs to tell the PROFIBUS network stop the motors immediately. You could use PROFIBUS to control different machines in the mining environment as well. So there's plenty of options as well. And that's not even talking about the process side of it, where you'd be looking at temperatures, pressures, levels of different stackers and whatever it might be. Can you do an online change as changing addresses without affecting the network? So yes and no. If a device is in data exchange, you typically cannot change the address of that device unless you take it out of data exchange. Now, there's 2 different ways of addressing. If you need to change the physical switches of a device, if you change the switches to a different device, then you actually need to power that device off and then power the device back on in order to take on that new address. If it's, for example, using a class 2 master to change the address, that device needs to be removed from the PLC configuration first. Then you can change the address over the network, whilst the class 2 master most likely will not allow you to change the address. Tumi asks, if I have one CPU on a rack, say an S7400, can I implement multiple networks by installing multiple communication cards in the rack? 100%. To me, that is actually the most common application which you see on site. You'd have a S7400, normally 3, 4, 5 CP cards, giving you 3, 4, 5 different networks, allowing you for a full conglomerate of what you need to do in that environment. Francis Mugarura, apologies for my terrible pronunciation, asks, I am 153-2 module configured but not available with SF and BF blinking. What could be the cause? So there's lots of different causes of why a device is not going into data exchange. SF and BF stands for system fault, bus fault. Bus fault typically indicates that a device isn't in data exchange with its controller at that given time. But the causes could be anything from a wrong configuration in the PLC, a wrong address set, to actual physical bus communication issues, such as a wiring short or fault. Ideally, you'd actually need to plug in a bus tester onto that network or connect the tester directly to the IM153.2 module to check whether he goes into data exchange directly or not. But Francis, please drop an email to Academy, send me your full case application of what's going on in that situation. If you do have a prof choice, send me your reports, and one of our engineers can definitely jump on that and see if we can assist you further from that. Okay, Anonymous said, I missed the part where you explained address 127, broadcast addresses. Can you please explain that again? Thank you. Okay, so address 127 is a broadcast address, which means that when a controller sends a telegram to address 127, every single slave device on the network will listen to that telegram and maybe action it. None of them will respond, but it uses two commands. It's called sync and freeze. And what that ultimately does is it allows devices to either pause the last received value which they got outside of normal data exchange, or unpause those different telegrams. Now I can give you an example. So if I sent a telegram of to pause all the start states of devices so they don't start at once. Say I have my conveyor belt, right? So I have 10 motors on my conveyor belt, and I want to start all 10 of those motors at once. Typically what I would do is I would pause so that they don't action any future telegrams I send them, so they pause their current state. Then in a normal exchange, I'll say start 1, start 2, start 3, start 4. Now, because those motors are in a pause state, they're not actually going to start, but they're going to receive that information and know that when I get an unpause, I'm going to start at once. Okay, so now I've sent my commands to all 10 stations. Then I could broadcast to 127 with a unpause. They've all received their start commands in the previous telegrams directly, and they'll all unpause and then all simultaneously start. That would be, I suppose, a typical example of where you would use address 127. Oh, great question. Jaden asked, is there a chance of having a distortion of the signal on Profibus at a distance of 50 centimeters apart from other communication cable? Thank you. So Jaden, I actually love that you asked that question. Another limitation in Profibus is the minimum length of cable between any two devices is 1 meter. So you cannot have less than 1 meter between any two devices. That just means that devices end up having an impedance impact on each other. So it's very important to have 1 meter between devices. That being said, if you only have two devices connected on a segment and there's 50 centimeters between them, I can imagine that the signal would be a little bit distorted. You need to make sure that you have two terminating resistors at those two different points at the beginning and the end of that 50 centimeter segment, but the cable should ultimately be at least 1 meter between it. Anonymous asked, how many people have attended this webinar? Right now there's 90 people on the webinar, but at one point it was about 108. So very fantastic turnout, and I think we're going to run a lot more events like this. Hope that you guys got a lot of value from it. Good question. Here's a good question. Is there a rule when assigning DOL, as soon as like digital outputs or digital modules, and BSD motors on a single network. So there's no general rule per se, but from experience, one very good advice that I can give is that you should generally create multiple segments or use segmentation to separate out different categories of devices on a network. And what I mean by that is by using a multi-channel repeater or repeaters, you should have your control systems onto one segment. For example, your PLC sit on one segment, they're completely isolated by themselves. You can take your I/O modules, your input-output modules, such as your ET stations or whatever it might be, put those onto a separate segment. Those tend to not be too noisy and don't interfere with the network. And then lastly, I would take motors, VSDs, and I'll put that onto a separate segment altogether. Motors, VSDs tend to be in a very noisy environment. Your Profibus cable is going to be running next to high voltage motor supply cables. It's going to be running next to the motors directly as well. So by putting those onto a separate segment is often good practice, and even multiple segmentations between those different motor segments as well. Thanks for that question. Anonymous asked, what does the DP and PA stand for? DP stands for decentralized periphery. So in my first example of the webinar, I spoke about a typical hardwired system where you have a central control station. All the sensors and actuators in the field are hardwired into that system. That's centralized periphery because all my peripheries are being centralized into one point. Decentralized periphery, I'm taking all my input and output receiving modules and decentralizing them across the plant. Profibus PA stands for process automation, I think. Yeah, process automation, typically because it's used in a process automation environment. Thanks, Anonymous. Okay, so Constant asked a good question. Thanks for the question, Constant. When you have a specific vendor PLC and another vendor Profibus or field device, who do you keep responsible for the GSD file to work? Okay, so it's the responsibility of the manufacturer of a Profibus device to give you that GSD file. The GSD file typically would be available on their websites. That being said, I know it's often very difficult to try and track down a GSD file, even more so when you're on a breakdown situation sitting on a mine in Rustenburg on your cell phone trying to download a GSD file. But the GSD file would typically be available on the website or on a CD or USB disk that comes with the device. And that GSD file is made by the device. The PLC itself will not really have a GSD file, but it will come with software where you can load the GSD file for those slave devices to give the PLC idea of what that device can do. The PLC will then take that GSD file, he'll parse that out or interpret it to give some more, and then give you all the information on how you can set that device up. All right, hey, Anonymous, see I've got this question third time. On slide 27, which signal is the repeater transferring? Let me see if I can find slide 27 quickly. Okay. So on slide 27, which signal is the repeater transferring? Okay, so let's send this live. Okay, so this is slide 27 over here. I've got my repeater down at the bottom. Profibus, as it's a bus system, everybody receives every single telegram. So as I mentioned, there's no routing. So I can't as a repeater and say, oh, I'm only going to take the messages meant for these slave devices. What this repeater is going to do, he's a bit of, I suppose you call him a dumb device, where he's going to say every single message that is received into me, I'm going to transfer out. So ultimately, whatever telegrams are sent by the master stations are going to come through the fiber. They're going to go into this segment. They're going to go through the fiber and they're going to go to this segment. All right. As it comes through here, the signal is going to be, I suppose you could call it split or repeated onto this new segment, and everybody's going to hear every telegram. Only the slave device whose address is referenced within that telegram is going to respond back up. And again, that respond is even going to be transmitted by the repeater. So the repeater is going to transmit every single segment on the network. Okay. Tumi asks, typically one installs a GST file in the IO config section of step 7 application that gets downloaded onto an S7400 CPU, right? Which will then be able to talk to a VEC drive as an example. Now I'm using a ControlLogix PLC. So typically all your PLCs will have a configuration station or PLC configuration station. Whether it's step 7, ControlLogix, we're using something from Yokogawa, ABB. All of the control systems work in a very similar fashion. And it's kind of the same steps to set up the network. I can't speak for every single vendor per se, but what I can do is give you a quick demonstration of how you would typically set up that PLC, from dragging in the GST file to setting the address to setting up the modules. Why don't we do that quickly? So why don't I quickly, okay, so let's go across to my useful Profi Captain. Okay, so this is an example of how most of the PLC configuration softwares would work. You would have a list of GST files down here in the middle. An example, I can have a look at my IO. Let's scroll down until we get to an ET200 station. It's great. Now, this is the actual GST file. I can see that the GST file name is referenced over here. I would simply just drag this onto my dashboard. Okay. Double click, and now you can see I have the ability to set the address of the device. So maybe my address in this case is address 54. My next, so now I've done two steps. Firstly, I've dragged in the GST file to make the PLC aware of what device I've connected to him. I've assigned an address to that device, so the PLC now knows where he can receive that device. My last step is I actually need to set up which modules I've configured on that device. Now remember, an ET station is a hardware modular device, which means there's multiple modules that have been connected to the device, and I need to tell that PLC which modules I've connected. So for example, maybe I have a 2 digital output card, then I have a 2 digital relay card, 4 digital input card, and the list could be analog to analog input cards, and so on and so forth. There's also some other user parameters that can be set up, module related parameters. So if I specifically want to, for example, configure my analog input card to be 4 to 20 milliamps or 0 to 10 volts, and how that behavior is to work. And the module would also sort of, I suppose, give you a description of what the GST file looks. So he gives me all the information from the GST file, which has actually been transferred to the PLC. And those are the only steps that are required. So whether that's done in ControlLogix software, Yokogawa, ABB, Siemens software, for their control systems, it's all the same process to get through there. Okay, good question. Anonymous asks, can you do an online change as changing addresses without affecting the network with a diagnostic tool? I can definitely do that. Why don't we do that now quickly? So the first step I'm going to do, let me just quickly do a class 2 command. I'm going to scan all the devices over here. I know that this device, address 11, I can actually physically change his address quite easily. Yeah, sorry, I just had to power cycle him and put him into, so it's quickly. Okay, so address 11, I can change him over the network. So I'm going to take 11 and let's maybe change him to address 45. Aha, I didn't actually set that, just 1 second. Okay, let's try that again. So now I've actually put him into a mode that allows me to change his address over the bus using a class 2 command. You can see now that I've rescanned the network. He's at address 126. 126 is my default address for devices outside of the box. So what I can do is change from 126, and I want to change them back to address 11 again. Hit change address, and station address change successful. Let's double check that. Do another scan, and true, he has been changed to 11. This could have been a live network which it is running on. What will typically happen is that when you change an address over the network, the class 2 command will wait for his turn in order to send that change address command. So he'll only do it within his token cycle. What is the shortest length of a segment? And that of slaves. So again, the only short or minimum required length for a segment is just going to be that 1 meter between devices. So I suppose if you had to have a PLC and just a single device, the shortest it could possibly be would be 1 meter. Makes sense? Derek asks, which system is best to use, Profibus or PROFINET? So that's a question that could keep us here for a few hours. But in summary, they are 2 different protocols. PROFINET has been developed by the same organization that actually developed the Profibus protocol. They're 2 completely different protocols altogether. PROFINET is Ethernet based. We're going to talk a little bit about Industrial Ethernet on Tuesday next week, and I hope you guys join for that. There's been a lot of useful features that have been implemented into Industrial Ethernet type technologies that you can take advantage of. That being said, I think that if you have new installations and new plants that you're considering on upgrading or that you're installing PROFINET is definitely an option, because PROFINET is a newer technology. It'll have more support from the vendors, but I would definitely not go throughout your Profibus networks because somebody is trying to force you to install PROFINET when your Profibus network is working perfectly. Profibus is very well developed. There's a huge amount of support base for a lot of different devices. If you can't get a particular device from one or so vendor, I would just go to another vendor and retrieve the device from them. I do believe that Profibus will be around for many years to come. So, and there will be a lot of support for it, and there's a lot of competent engineers that know how to work with Profibus systems as well. But installing PROFINET on your systems, definitely I would consider moving to Industrial Ethernet, but making sure you understand the Industrial Ethernet protocols as well, and not taking that leap without having the question. Thanks for that question, Derek. Okay. Are you able to communicate 4 to 20 milliamp signals over a Profibus network? Thanks for the question, Andre. Yes, 100% you are. You can send any data across a Profibus network that you choose. Your only limitation on a single telegram of Profibus is 244 bytes of data. So typical, if you had to slot a 4 to 20 milliamp signal, maybe that'd be put into a floating point, which would take up 4 bytes of data. So you could send quite a few analog signals over a Profibus network. But again, any data you would want to send over a Profibus network, you're able to do if the device supports it. Profibus DP version 1 also allows a mechanism to define data types across the network as well, which can, for example, send through like floating points and large integer numbers as well. So you can get quite a high resolution of data across the network and recognition of that resolution as well. Can a repeater be used for 2 different networks? Sent by Anonymous. Okay, can a repeater be used for 2 different networks? So I don't fully understand the question, but from how I interpret it is, can I connect 2 different networks into one repeater? No, definitely not. A repeater is a passive component, which means he doesn't have any routing, so he's not sure any binary string or electrical signal that goes into a repeater is simply going to be transferred out into other channels. Now, if you have 2 different networks connected into a repeater, you probably just going to end up having a clash of the networks. There probably wouldn't be an issue if you connect to the networks, provided you have unique addresses on the 2 different networks and the 2 different networks are operating at the same baud rate. Then you ultimately wouldn't have 2 different networks, you'd actually be creating one network. So a repeater will ultimately be linking networks into one single network. If you want to connect 2 different networks but keep those networks separate from each other, you need to use something like a DP-DP coupler, which acts as a slave device on each single segment. Okay, so Marius has asked us, solid core cable or stranded? Also, instead of the standard purple cable, you get oil and UV resistant cables for each application. Maybe just run us through the different types. All right, so solid core must be used in static environments. You can't bend solid core very much. A good example of this is if you had to take a paper clip and bend the paper clip 10 times, that paper clip's eventually going to snap. So if you want to install a cable in an environment that's moving, for example, an energy chain on a crane, that needs to be stranded core. I would use solid core for every other application because it's lower cost and easy to integrate into. And as for the different types of covers on Profibus cable, purely dependent on your application. If you're going to be connecting a whole lot of actuators around a sewage plant, for example, and it's running out in the open, then you probably need UV resistant cable that can be protected from the sun and doesn't deteriorate. Generally, if you're running underground, you want armored cable. So all of these have different costs associated to them where cables can get very expensive. So you don't typically want to use the wrong cable for the wrong application if it's over-engineered for that application. 9 times out of 10, just using basic solid core cable costs you probably around 15 to 20 Rand a meter of cable is perfectly acceptable. Okay, Anonymous asks, could you give us a brief overview of DPV0 versus DPV1 versus DPV2? What is acyclic data? I guess that is a good question. These are different standards that were released by the Profibus protocol. So the first one they released was Profibus DPV0. Now, all of these protocols are completely interoperable with each other. DPV0 allows for diagnostic data, it allows for parameterization and standard cyclic data exchange, so where devices can send and receive data from each other. And then the Profibus organization realized that there was some void in the protocol that needed to be improved on. So what they did is they released DPV1. And what DPV1 did is it integrated a mechanism for alarming. Now, the main difference between alarming and diagnostics is alarming actually requires acknowledgement of a problem. So within DPV1, what happened is if a device says, my digital inputs line 6 is a short circuit, so I'm going to send an alarm, the PLC or a physical operator would actually have to go acknowledge that alarm in order for the alarm to clear. DPV1 also released data types, so I could actually, within the Profibus protocol specification, define data types of different submodules. So, for example, floating points associated with analog input cards, time of day, and so on and so forth. And then there was also some more information integrated into downloading and uploading large amounts of data between different stations. For example, if you wanted to upload a recipe into a particular plant, a recipe to make bricks. So maybe you have a system that can make 10 different types of bricks. You want to upload large amounts of data. It included a mechanism for something called slots and indices that allowed you to upload and download large amounts of data on the network. What is acyclic data? Okay, so let's first talk about cyclic data. Cyclic data is the standard PLC slave control, right? So where PLC can talk to a slave device and can receive the information back. So read inputs, make a decision, write outputs. And that happens without any human interaction. It happens as soon as you turn on a PLC, immediately cyclic data is going to occur. Acyclic data requires what we call human interaction. So I physically, as a user, have to go and click a button for that action to happen. An example of an acyclic data would be where I went and set the address of my device earlier. That was an acyclic command. It didn't happen on its own. I had to physically send that command out onto the Profibus network. Acyclic data is typically used by class 2 masters or for class 2 master type functionality. Thanks, Anonymous. Okay, so Joseph asked, sorry, you have said the minimum length between devices is 1 meter. There are some in here that have less than that. Does this have a technical effect? Yes, it does. It's definitely not a showstopper, and I wouldn't stop your plant right away to go and correct all the problems, but I definitely would schedule into maintenance to increase that distance between devices. It does have a technical effect. What happens is devices start having an impact on each other, and you end up seeing like a little bit of a spike in the signal waveform. This is definitely not going to trip your network if it is the only fault that is on your network, but if you add that onto a missing termination, along with a duplicate address, along with EMI, it's just going to be another nail in the coffin to the PROFIBUS network. So it's probably good practice to remove that when you have scheduled maintenance once a year or whatever it might be. Oh, Wayne, just a comment, DOL stands for direct online motors. Thanks, Wayne. I don't have too much knowledge on that, unfortunately. Thanks for updating me. Can fiber used on slaves instead of Profibus? Okay, so that's a good question. I think he's asking, can I connect fiber directly to a slave device without using an OLM? Yes, 100%. I've seen that in the past with large actuators out in the field and very large VSDs, so massive or soft starters, massive soft starters that have a direct fiber input and don't actually have a mechanism to connect in RS-485. That would integrate into your Profibus network just with a simple OLM on the other end of it via copper. So yes, 100%. What is the importance of multiple masters in one Profibus network? Okay, so the main reason for having multiple masters is two different reasons. So one would be to create a level of segregation or segmentation on the network. If you had to, for example, take a mine example, maybe you'd have one PLC for above ground operations and another PLC for below ground operations. Another reason for using multiple PLCs might be the computational power of the PLC limitations could be an example. And maybe different functions of masters as well. A good example is maybe you'd have a central controlling master, the main PLC that controls all the devices on a large network. Then you could have an HMI. An HMI can act as a master as well on the network. And maybe that HMI is used to control an individual device, so maybe move a hoist left or right. The main PLC still needs to have some indication of what state that hoist is in or what state that HMI is in, but the HMI can be a separate master on the same network as well. Okay, Stephen said, I believe this will be discussed in the earthing session, but how important is earthing of metal conduiting, i.e. conduit piping? Absolutely critical. If you're going to be using steel or aluminium conduits in the field to run your industrial communications in, that steel or aluminium conduit has to be grounded at multiple different points across the network. And it'll be completely useless if it is not grounded. And the main reason is that when EMI is injected onto that steel conduit, which is protecting your signal in the below, that still needs a mechanism to drain that interference to ground at some point. So 100% critical to ground steel conduiting. All right, thanks, Dave. Remote I/O devices often are configurable with one or more digital or analog cards. Is this a sort of configuration that goes into a GST file? So the PLC master needs to configure the device to match a module used. Yes, Dave, thanks for the question. So if you have a certain I/O device or module has multiple different cards, you need to tell the PLC what that device is being configured as. The PLC will then do a check with the device to ensure that what you programmed and told them to do is the same as what the device physically has installed on him as well. So that's done in part of the configuration process, so dragging the GST file and assigning the specific submodules within there. Okay, Anonymous asked, even if a device is not connected or address is not configured, will the Profibus master scan for that address? So yes, on both questions. So the first part of the question, if a device is not connected to the network, but the PLC is being programmed to look for that address, then yes, every single cycle the PLC will go around and try and talk to that device. If the device wants to respond, he will move on to the rest of the network. If a device is not configured on the PLC, all right, but it is physically available on the network, then the master will, what I mentioned earlier was FTL status request, which is what we call a ping. The master will ping that device and identify that that device is there. He will not do anything with the device, so he'll purely just go around and check the device. What the master is actually doing with that ping is he's looking for other masters, so to check whether he can hand the token to anybody else. But he will be able to ping that device and show him up on a live list. So an example which I have, if I can just switch my screen quickly. In this scenario over here, on my PROFICHase screen, you can see that I have these 3 devices. They're connected to my network. I can see with the blue dot that they are connected, but they're not actually in Data Exchange. I'll only see them in Data Exchange if there's a green block over here. And the same thing if I actually look at the physical messages, I can see that the master is sending these ping messages throughout the entire network, or what we call FTL status requests, to every single device, all the way from 1 up to 128. Right? And then you can see where he's just passing the token to himself because there's no other masters to pass the token to. If I had to configure one of those devices, so for example, let's take our device 11. Right. There we go. Set him to device 11. Let's quickly assign a module. So I'm telling the master what module can actually be, what he can do with this device. He can read 4 bits of I/O from him, 1 input and 1 output byte. Okay. Make him active. He goes green, that means he's online. Again, now I can see that the PLC has been configured and programmed for this device. He's still checking these devices are here, but he's actually in Data Exchange with that device. So now if I stop a message recording again, I can actually see the data message. He's actually sending data to and from 11 and receiving data back from 11. Okay. But he's still sending his ping messages throughout the network. Anonymous asks, briefly explain how redundancy systems work within a PROFIBUS network. So again, another topic that we can spend a lot of time talking about with regards to redundancy. There's lots of different levels of redundancy when it comes to a PROFIBUS network. A lot of caution needs to be taken when implementing these redundant networks. The most common redundant that is configured would be redundancy on fiber optics, where you create a fiber optic ring, where you have 3 or more fiber optic modules, and you connect them all together in one big circle. And the main reason behind that is because of how long the fiber cables run between different sections of the plants and the environments they run in. If one fiber optic cable gets damaged, at least it has another route to connect to the different subsections and segments. Other levels of redundancy, you might have redundant masters, and you could use something like a Y-link module or a master redundancy switch. And what would happen is if a master fails for whatsoever reason or gets damaged, it will immediately switch over to the other master in order to take over communications. Then you get redundancy on RS-45 segments. You can use something like Profi hubs or multi-channel repeaters to connect to the to run redundant RS-45 links between different substations. So if I had a Profi hub over here and a Profi hub over here, I could run 3 or 4 redundant copper cables between those two different substations. And what the Profi hubs will do is, if it detects one cable is interfering, he can immediately swap over to one of the other cables. So lots of different redundancy considerations, but I think what's better is what is your application and what is the level of redundancy and the importance of that device remaining alive. Do you need redundant devices, redundant control systems, or redundant transmission technologies? But you're welcome to always drop an email to academy@IDX, and we're always happy to assist with device or network setup as well. Okay, Tashwari, Swari asked the question, what is the difference between DP and PA pertaining to their max speed, max packet sizes, bus power, and medias they use? Okay, so for let's go through it quickly. For DP, my max speed is 12 megabits per second. It's configurable. For PA, it is not configurable. It's fixed to a very slow baud rate of 31.25 kilobits per second, so it's a very slow network speed. I cannot configure the speed on a PA network. Packet size is about the same, 244 bytes of input and output data. Bus power, there is no power on a DP network, but a PA network, depending on the type of PA coupler you use, could be anything from 200 milliamps to 1 amp, I suppose, of devices, and that would work in a similar way to standard DC power supply, where you need to make sure that all the devices connected on that bus do not exceed the power output of that coupler. Medias they use, DP typically uses RS-485 and fiber optics. PA always uses MBP-IS, which stands for Manchester Bus Powered, for intrinsic safety. It's a completely different technology to RS-485. RS-485, which is used in a DP network, uses a voltage switching mechanism to transfer binary data across the network. So basically switching a voltage on and off to get us those ones and zeros across the network, whereas PA uses a current switching technology, where it switches between a positive 9 milliamps and negative 9 milliamps to transfer the binary data, but it keeps a constant voltage because it needs to power devices on the network. The voltage which is across the network would be anywhere between 9 and about 30 volts DC, I guess. Here's a question: would anybody be interested in a talk on PROFIBUS PA, something similar to this? I don't know how much, I suppose the breweries would have quite a lot of PA. So if you guys are interested, drop me an email to Academy, and yeah, something we can definitely set up as another webinar session. Seems to be a few PA interesting questions, so yeah, happy to jump on that. So the question is, what are we trying to achieve to interconnect different Profibus networks through fiber optics networks? Okay, so Profibus I would typically use if I'm connecting one network to a large area of the plant. It's not such an issue if you have just a single substation, couple of panels. I don't really need to use fiber optics. I can simply run copper cable between all those different panels. But if I have a, for example, central control station where I have all my PLCs, and then I have substations and rear panels distributed throughout the entire plant, possibly kilometers away or hundreds of meters away, it makes more sense to run fiber optics to those sections. And the reason being is because fiber optics can run longer distances than RS-485. It's also immune to noise and interference, so that's where fiber optics is a better choice as well. Is the following correct? 244 bytes IO, 416 bytes in total is limited to each Profibus DP node on the network. That means that the whole PA network is limited to 244 bytes in total, as it is seen on one DP node. Can you please explain this a bit more? So what the question is asking, okay, so this is actually a good question. Right, so 244 bytes of input and 244 bytes of output is the maximum telegram length per device, which means that if I have a single device, call it a VSD, the maximum amount of input data from the device to the PLC cannot exceed 244 bytes in length, which means that my cyclic data, which is going to that device and coming from that device, cannot exceed 244 out, 244 in. The 416 bytes limitation, I think that's a limitation probably related to like a gateway or IO module specifically on that network. The whole PA network is limited to 244 bytes. So what Stephen is referring to there is the device that connects a DP network to a PA network, which is called a coupler. And that device has two ways of operating. Either it can act as a slave on the DP network, which means that it would have a single address, which, yes, in that case, it would have a maximum of 244 bytes of input and output data, which means that anything connected below that PA coupler slave device could not exceed 244 bytes together. But That being said, you also get other PA couplers that allow pass-through, so which means that the DP controller can go straight through the device. The PA coupler would be transparent, which means you can probably have a much more larger amount of data than 244 bytes of data. But yeah, a good question. Thanks, Stephen. If you have two networks, can you communicate between the two networks via Profibus? You can. You'd need to use a DP-DP coupler, but more often than not, the communication between the networks is enabled through the control systems and through a high-level type system as well. But using DP-DP coupler, which acts as a slave on either side, will allow sharing of input and output data that needs to be configured. So I have another question. How can we receive the course material since some of us are logged on anonymously? So a lot of you have RSVP'd into our Academy webpage where I have an Excel sheet, which I will send all the communication to after this in the course material, after this course. But if you have joined us without RSVPing just because you got a link from one of your colleagues, welcome, thank you for joining. But then just drop an email to Academy and just say, hi, I'm John. Can you please send me the course material from your webinar? And we'll happily add you that list and send it through. Your email is obviously fully confidential with us, and I'm not going to use that to spam you apart from send you some useful information. Thank you, sir. Okay, so Christian, thanks for joining us, Christian. Asked the question. We specify the baud rate when we do the device configuration on the PLC. If I change my baud rate on the PLC from 1.5 to 3 megabits per second, how does the slave device know to change to the new baud rate? Does it check the different baud rates until it finds something? Yes, Christian, that's exactly it. So the baud rate is only normally configured in one place, which is the PLC. That being said, there are sometimes network components that require you to hard code the baud rate. Some repeaters and optical link modules require you to actually indicate the baud rate on switches. But if you change the baud rate from 1.5 to 3 megabits per second, you would have to stop the PLC communications in order to download or enable that change. And on startup, the first message that is transferred to the slave device will detect the baud rate, probably based on the bit length, I assume. And he would conform to that baud rate and respond at that baud rate per se. Thanks for the question. But we are going a little bit over time now. So any more of your questions, please do drop the questions into Academy at IDX. I think I'm also going to get download of these questions, so if I can identify you and you didn't post them on anonymous, I'll respond to you by email after the session. If you have any more questions, please drop them to Academy. There's myself and two of the other engineers who work with me in Academy, Bruce and Sean. On Training Academy, who will respond to you shortly and give you advice. But yeah, hopefully I will see you guys on Tuesday. Thank you so much for joining. It's been a great event. I think it went very well. And I hope that you all got value. I hope that you all stay safe and healthy, and all the best. Thank you so much, guys. Cheers.